Hello, this is Pat Hindle, Technical Editor at Microwave Journal. It is my pleasure to welcome you all to this session in our Technical Education webinar series on filtering solutions for improving dynamic range of intermodulation distortion, intermodulation, and triple beat testing for 3G, 4G, and LTE systems and applications. Before we start, there are a few items that I'd like to bring to the attention of our viewers. Today's presentation is approximately 45 minutes long, after which time we'll hold a 15-minute question and answer session with our presenter. You may submit a question through the website at any time during the presentation through the Q&A box.
100.
We will hold the questions to the end of the presentation is complete, and please address your questions to all presenters, which is the default setting in the Q&A box. The presentation will be archived and be able to be viewed online later on demand on the events section of the Microwave Journal website. Also, if you'd like to see additional details on the slides, simply click on the Enlarge button in the lower left-hand corner. Today's webinar is presented by K&L Microwave and will discuss several innovative filtering solutions to minimize or eliminate the use of attenuators while increasing the system's overall return loss. Together, these approaches significantly increase the dynamic range of any test setup. Our presenter today is Rafi Hershtig, Vice President of Advanced Component Engineering at K&L Microwave. Rafi received a bachelor's degree in electrical engineering from Ben Gurion University in Israel. From 1985 to 1989, he worked for the microwave department of ELTA, focusing on the development of switch filter banks and switch multiplexers. In 1989, Rafi joined K&L Microwave and worked on the development of filter-based subsystems. Since 1992, he has focused on research and the design of new product lines, including the printed filters in the SSS form and dielectric resonator filters. He has been involved with K&L's wireless application group since 1995, designing high-Q elliptic response filters and delay line assemblies with the in-house design program CKT tool. In 2001, Rafi received a master's science degree in wireless communications from NTU. And much of the last decade has been dedicated to serving the military market, producing high-power, small-volume filter assemblies, surface mount filters, and multiplexers. Research in mixed technologies has yielded high-pass and low-pass filters with very sharp roll-off. Support of the commercial market has included the development of low PIM filtering solutions and addressing 4G-LTE testing needs. In addition, Rafi holds 6 patents. So at this point, I'd like to hand off the webinar to Rafi.
I'm excited to be here. And today's presentation, we'll be talking about filtering modules for the IMD measurements as Pat mentioned. Our objective today is to talk about typical IMD levels and applications. Emission monitoring solution, we are going to present how to measure without disrupting. Then we are going to look into a toolbox of solutions, low PIM filtering solutions. They are the building blocks for reducing uncertainty of measurements. Among them, the high-pass, low-pass duplexer, the band-pass, band-stop duplexers, band-pass, band-pass duplexers, triplexers, band reject filters, etc. Each one of these block diagrams is going to play an important role in improving the dynamic range of the future test system. Build your own IMD test setup is almost inevitable. As of today, everything is gearing towards injecting multiple signals into the device and the test, and sometimes to both sides of the device and the test, and it's hard to find one push-button system that does it all. The next topic would be the blockers are everywhere. Blockers, interferers, aka jammers, are representing other systems next to 4G that are geographically residing nearby and are usually interfering in the receive band of our system. We will introduce the quadruplexer for that reason. Then we're going to take everything we learned or been exposed to this information thus far, and we'll apply it to a triple bit test. And we're going to look at a real challenge. We will see a block diagram. We will try to improve it. We will look at a roadmap to a complete and customized switch test system. I want to emphasize customized. We have many devices under tested with different characteristics, and it's going to be hard to find one common denominator, so customization is a key. Q&A at the end, and I hope everybody will have a good time. Okay, before we start, let's just have a common denominator of expressions and numbers. The typical IMD levels that we are going to focus here are going to be created by two tones, usually in the TX band. So since the third level is the most critical, we're going to refer to the third level as representative of all IMs. So the IM third is 2 times F1 minus F2 and 2 times F2 minus F1. The equations, the expressions on the right-hand side are, you should all be familiar with. And then we have expression like PIM. PIM is just IM that was created by a passive source. So given all these parameters, it's best to ask everybody before they publish or before they talk about any topic to give enough numbers so we can see this diagram in front of our eyes. Applications, 2 tones plus 43 minus 113 dBm usually is good for base station, PAs, antenna manufacturers, measurement. In short, we call them the high power guys. 2 times 43 minus 18, a little bit, minus 118, a little bit deeper. DAS systems usually looking for. And then we have a set of applications that are calling for 2 times 26 dBm or 16 or minus 16 dBm. And these are represented by the semiconductor industry application, the small cell, chipset, switches, tunable caps, etc. And then PIM analyzers that we often see, they really require the filters to be about 171 dBc. The rate of change of the third intermodulation product by the literature is 3 dB for 1 dBm reduction on both carriers. I here state that empirically speaking, I would like to use a factor of 2.2 dBm for every 1 dB reduction in IM. So if we look at these two main applications, the high power and the low power, let's just do a quick check and see how far are they from each other or which measurement is tougher than the other. So what we want to do, we take the 113 dBm and we lower the carrier powers from plus 43 to plus 26. Simply minus 113 minus 2.2 times the difference, and the response is minus 150 dBm compared to minus 140 dBm. What I'm trying to point out that that the base station application is a tougher requirement, the high power is tougher requirement than the low power, but only by 10 dBm, which means we can use the same technology solution for high power as for low power. We're going to dive into the first setup, and every time we see a setup and a possible solution, we're going to then go in and get more information. Our first task is to monitor an emission that comes from any device, any power, usually has a shape like this, and we recognize the near zone and the far zone. The task here is to measure everything, say, from DC to 13 gigahertz. This is the set of filters that is recommended for such a setup. We have a high pass and a low pass. The low pass takes care of the near zone. The high pass takes care of the far zone. And in the near zone, we see a new diplexer, band pass band stop configuration. Here we terminate the band pass with a low PIM termination. From now on, noted with the red star. In reference, for instance, when we don't need a low PIM termination, you will see that the red star was taken out. We will talk about it more. The spectrum analyzer with an SPDT will complete the task by switching in and out, one time to measure the intermodulation in the near zone and one time to measure the far zone intermodulation. The SPDT is non-reflective. Talking about bandpass bandstops, if we look at a bandpass bandstop and terminate the bandpass, then the S11 is matched. The S11 is matched as a band reject filter. As a band reject filter, if we terminate the bandpass, the S11 is matched. The same effect we can achieve if we put an attenuator in front of a band reject. And as Pat already talked about in his presentation, in early presentation, that this attenuator eventually will reduce the dynamic range of the setup. So everywhere, every time you have a configuration of an attenuator band reject in your schematics, I recommend that you think about replacing it with a bandpass bandstop, terminate it, and get yourself back the dynamic range that was taken by the attenuator. On the same token, if we terminate the band reject and we look into this diplexer, then the S11 common is matched for the bandpass filter. Again, attenuator in front of a bandpass filter is equivalent. So these are two identical solutions that might give you a larger dynamic range. As a third note here at the bottom, this application is not related so much for what we're speaking today, but you can take a TDD system and an FDD system and combine them both into one common antenna using a bandpass bandstop configuration. Great thing about TDD that we don't have IM. We don't have IM in TDD. More information about bandpass bandstops can be found on this link here. And we have developed bandpass bandstops for nearly all the LTE bands and all the possibilities in combination within LTE bands. As you can see, this is a cavity filter, and it is handling more than 100 watts for 150 watts CW and a couple of kilowatts peak with 10% duty cycle. Data is attached to the website, and I'm not going to spend too much time. You can do it by yourself later on. The bandpass bandstop is also, each bandpass bandstop is also measured for PIM. And what I would like to mention here is that the shape of the PIM of the results sometimes can indicate of what's going on inside. The flatter the PIM response, the fewer the IMD sources. And here we're starting to talk about mismatches, VSWR mismatches, IMD sources. They can come in phase and out of phase with each other and give you a baseline before you insert your device on the test that can then reflect in very deep deeps, 20, 30 dB deeps, even though it's a point that you would like to read. Bear in mind it's probably caused by another IMD that was out of phase with your device on the test. Important to remember the fact of matching, VSWR matching, and IMD sources. Another element that was in the previous diagram was the high-pass, low-pass duplexer. One application was the emission monitor application. The second application is second and third harmonic test. We have a PA, we have a device on the test, and we would like to inject high power, single tone, and we would like to see second and third harmonic through the spectrum analyzer using high-pass, low-passes, terminating the high-pass. Right after the PA, will guarantee that no second harmonics from the PA, which we know are created, will go through the device on the test. That's the purpose of this high-pass filter here. And this high-pass will reject the carrier from burning or mixing into the spectrum analyzer. More data can be found on the internet about high-pass, low-pass, low-PIM duplexers. You can just use the same link that was mentioned before. Typical data, again, taking data, PIM data for every unit that is being shipped, and in general, the low pass has 50 dB rejection, and the high pass has 90 dB rejection. Remember, the high pass needs to reject the carriers from going into a spectrum analyzer. Let's talk about IMDs in the RX band. IMDs created by two tones in the TX band, setup 1A. I didn't put this setup here because I like it. I put this setup here to get over and remove it from the table. Basically, we are combining two signals into a single amplifier. This is a single amplifier setup. I personally think that this has a disadvantage over two amplifiers. Well, you see that we will see next. And so we're using a duplexer before the device under test and a duplexer after the device under test. The two carriers are going through the TX. And here we are measuring reflective and forward PIM from the device under test. The reason I don't like this one that much is because we know this amplifier is going to produce two TX1 and TX2 signal, but also the intermodulation product probably 35 to 40 dBc down from carriers if it's not linearized or optimized, etc., which is the big honk amplifier in the back of our labs. Therefore, it will send into the TX filter harmonics, and now the TX filter will have to have a lot of rejection, maybe close to minus 115 dBc, in order to support a decent baseline that we mentioned in our application slide. Note the low PIM termination at the end of the TX. We don't want to have the third intermodulation product that might come back, and this setup is for a very large dynamic range, so every bit counts. The same token, if we take out the output side, we can just stay into a reflective mode, and that's all we have here, into a reflective mode. Again, the duplexer has to be a very high quality duplexer to do these things. Let's switch to two amplifiers. This is, again, IMD in the RX band, and now we are combining two amplifiers. This is a very cheap and broadband and popular setup by engineers, and there are couplers that will cover 700 to 3500 megahertz, 3 dB I mean, and so two amplifiers, a 3 dB hybrid into a TX RX. Very important to have a low PIM termination at this port, as carriers will mix here and they can also be reflected back. So it's important to have a low PIM termination here. A low PIM termination also here at the end of the TX. These TX RX duplexers, I will send you data. You can download the data from the internet. The one drawback, probably a limiting factor of this setup, is that let's think about if it's WR match. Device under test might be in the order of, say, 10 to 14 dB return loss. The TX filter, we can guarantee that it is high quality, so better than 20 dB return loss. So when we place an isolator here and a coupler, we think that we're going to get 22 dBs from the isolator, maybe another 22 dBs from the coupler, and then we have amplifiers that mathematically are 44 dBs, let's say 40 dB to be on the safe side. But then what happens is that the return loss here that can be degraded from 20 dB all the way down to, say, 13 dB return loss below the return loss of the device under test is sending the TX1 and TX2 powers back into this area here on the left. So TX1 comes from here, TX2 comes from there, but when they reflect back, they are equally split. So now we have IMD sources here and here. So if we're not careful with the amount of the rejection that the TX filter will have, we have in this area IMD sources that will come in phase or out of phase with the IMD sources from the device under test that might give us a faulty reading. And this whole setup here probably has a limiting dynamic range that we should be aware of. A shorter way is to disconnect the right-hand side and to look into a TXRX device under test only in a reflected mode. This is also an option. Bear in mind that your gain from the TX amplifiers will have to compensate for about 3.5 dBs for this junction here. So we are driving the amplifiers a little bit harder. Instead, we can offer replacing the 3 dB hybrid with a TX1 and TX2 duplexer and achieving 75 dB of rejection. We can guarantee that. Placing the isolators is an option. Sometimes you would like to place, sometimes it doesn't matter. Depends on your setup. The low PIM termination here is terminating the TX. The two filters are going through the TX. Note that this is a TX, this is TX1, TX2, so this filter is wide enough to pass both carriers through the termination, and then this is our receive band. So this is a good option. And what's missing here, it's the only maybe a drawback, and that will lead us to other solution is how do we debug this thing? How do we make sure in the lab that the reading that we don't like is coming from the device under test or from the network itself? Of course, we can take this device under test out and look at a direct connection, but we really don't know if the problem is at this junction or problem is at this junction. From passive components point of view, this port here and this port here are quite cold in terms of IMD sources, but this port here is very hot. The reason is there's no TX2 here and there's no TX1 here, so there's really no problem even to place here an isolator, which is a ferrite ferromagnetic device and an IMD source. More information about BEMPAS filters with 100 dB isolation from TX to RX and 161 dB CP for plus 43 dBm two-tone can be found on this link on the internet. To overcome the problem that we mentioned before, we are introducing a new device, which is a TX1, TX2 RX combo. By the way, every time you see a red dashed line, that means that it's all included in one unit. So you have no access to anything inside. All you see are the connectors on the outside of the unit. We make sure that all these manifolds are low PIM manifolds. So we are introducing here a new filter solution that will combine TX1 and TX2 and the RX, and on the same token on the output of the device and the test. Note that there is no reason to put a low PIM termination at the output of TX1, TX2, because again, there's no TX2 here and there's no TX1 here. So identical units can also reduce the cost of your setup. Placing a non-reflective SPDT spectrum analyzer can complete the task to give you reverse and forward. Debugging this test setup is easy. All we have to do is put a low PIM termination here, and we make sure that this triplexer is good. We can do the same thing about this triplexer. We know every component is good before we install the device under test. Another tip, you can put here a transfer switch and connect a network analyzer right beside this. And now you can also characterize your device under test, download S parameters, and do all kind of stuff. More information about this BEMPAS Triplexer can be found on this website here. And we have developed about 7 or 8 LTE bands duplexers. We are now opening a chapter where we have to hit the device under test from both sides. Up to now, we saw in that the carriers went into one port of the device under test and exited from the other side. But we're all aware that there are many applications where a TX signal needs to hit from the input side, and another signal, interference signal, a blocker signal, etc., needs to be injected from another side. By the way, see that this amplifier here is reversed. So just change the polarity of this isolator. I don't know how we let that go through like that. Okay, move on. So we are now going to discuss from now on where we are injecting signals from both sides of the device under test. This setup is, I'm not aware of any setup right now on the industry that will allow you to inject signals from both sides. All I know, say the PIM analyzers, the carriers are coming through one cable, one connector. For that, we have developed a low PIM triplexer where we take the download band and we cut it in 3 parts, TX1 and TX2, and then we allocate a BEMPAS filter for the receive band. So we make sure that this download band is a typical download band from an LTE well-known frequencies, but every combination from between F3 and F4 and F5 and F6, every combination will yield an IMD only in the receive band. So we're not addressing here solutions where we are looking for IMDs in the TX band. For that, I would say we'll have a different webinar sometime in the future. So this low PIM triplexer is operating this way, and more information can be found on the net. We all know that the blockers can extend from DC to sometimes 6 gigahertz. It's different for every LTE band. And we would like to introduce a new filter solution. This filter solution is a TX-RX band reject. The band reject rejects the TX and RX bands altogether, but allows you to inject blockers on the low passband and on the upper passband. Why do I call it a quadruplexer when it's only 3 ports triplexer? You will see in the next slide. I will just hint and say that since the blockers are everywhere, up to 6 gigahertz and above, some of the band rejects will not hold an upper passband that will match the blockers frequencies all the way to 6 gigahertz. And for that, we will have to look at the following solution. So what we do here, we are offering a filter solution that we extend the band of the upper side of the band reject by introducing a low pass and a band pass. This band pass will allow you to inject blockers from the signal generator that are on the higher side of the list, which cannot go from the input to the band reject filter. And so this new unit now is also available for every LTE band. Note that there is a low PIM termination on the output of the device under test. So by doing that, we inject a TX in the TX band. We inject an RX through the VRF, band reject, or through this path, and we are measuring the reflected mode. So this is a reverse or reflected IMD measurement. Test data are also available on the internet. All the matching are quality of 20 dB return loss. We have 75 dB rejection between the band passes and the band reject filters. These are actual data of 2 band pass blockers that are connected to the low-pass filter. And these are measurements that we took to make sure we can guarantee minus 140 dBm for plus 26 TX1, plus 16 TX2. I believe that we can push that even further down to minus 145 in a short time, just by incorporating everything that we learned from the high power solutions. And these are more data that we took, and as you can see, it's well below minus 140 dBm. Minus 140 dBm is your setup. That's not to say that your device under test is minus 140. So these are margins on top of margins, and that's important to remember. Let's look at an LTE case study where we take band 2, LTE band 2. By the way, what you can do when you download this presentation, you can just highlight or take a snapshot from the presentation, send it to us, and say, I want that on LTE band 7. And we will generate the specs for you and will tell you what that component should work and go over the spec and see if you need to modify it a little bit or if you like it. And that's how we're going to do that. So case study, LTE band 2, we noting the bands. This is the blocker, 80 megahertz, and here blockers, and here blockers, and here. Obviously, a band reject cannot hold all the way to 6 gigahertz, so we are introducing this low-pass band pass on the left to do that. This is what we have. We have a TX, RX, and BRF. This is the blocker signal generator, and this is the setup 6A. So setup 6A is for the cases where we can squeeze some of the LTE bands. We don't need a low-pass band-pass duplexer to extend the band. Some LTE bands we need, depends. So this is a case where the blocker can be injected from the BRF from this side and the TX from that side. Again, SPDT to measure reflected and forward measurement. I kind of forgot to mention that in all my setups, I kind of made it simple, and I did not include all the couplers that we put to measure reverse and forward powers, etc. So just for simplicity, you might have your own couplers here that validate that indeed the power is flowing through. This is a complete test that will allow you to put all the blockers list for reverse, for and for forward, but with another benefit. We can do here port swapping. In other words, we can switch the direction of the TX and the blocker. So we can do a TX from here and a blocker from here, or a TX from here and a blocker from here. Some of your devices might not even need that, and some of the devices where we have some directivity might need that. So this is the case where you don't have to literally disconnect and connect again the device on the test by allowing you to do port swapping. Everything we said thus far gives you the freedom to choose your own destiny of your IMD, and by mixing and matching solutions that we covered thus far, So I just put few of them, few slides together that shows that you can mix and match from all the various types of setups. Before we move into the triple bit and the third IMD for RF switches and other device under test, I would like to kind of recap what we've been talking so far. So we had the BEMPAS that gives you the ability to isolate the amplifiers, the BEMPAS band stop that gives you the ability to put matching, S11 matching, high pass, low passes. And now what I would like to do is use a National Instruments published white paper that is available on this website. And I would like to take their setup and kind of put in the flavors of everything that we learned thus far. So we have in this measurement, we have 2 TX signals in the download band, mobile uplink, and we have a receive filter. We have a receive jammer right into the receive band. Again, 3 signals, TX1 and TX2. So we are looking at the National Instrument test setup. First thing, we observe the 2 amplifiers with the 3 dB hybrid, and so we remember what we said about that. And then we see a duplexer here. Probably the TX will have to have a lot of rejection to block IMDs that are being created here. And then we see here a jammer that injects the signal into the device under test on the opposite port. What we see also is that the TX signal that goes into the device under test actually has nowhere to go but into the jammer source. So that's something that should bother us. What does the signals going into a jammer source might also mix again, and then this whole thing is going to be loaded with IMD sources. And then we follow the jammer source, and we see that it goes into our spectrum analyzer. So we don't want signals to go into spectrum analyzers and into sources. So we have a 1, 2, 3 phase solution with what we learned so far. In phase 1, we maintain the coupler isolator and the duplexer, but we take the transmit signals from going into the blocker source and we terminate it through the TX filter by using a TXRX duplexer. That's phase 1. In phase 2, we are getting rid of the 3 dB hybrid, and we are gaining back 3.5 dBs. And now we are using one of our triplexers here, and all alone maintaining the duplexer and terminated into the BEMPAS. So what's missing? Phase 3. The phase 3 was that this signal goes into the device under test and into the spectrum analyzer still in phase 2 solution. Now, depends on the level of the jammer and the IP3 of the spectrum analyzer, we might end the required dynamic range. We might say, hey, it's okay, it's fine, it's fine. But bear in mind, again, IMD sources tend to go phase and out of phase and every phase in between with your device under test, so you really don't know. The final vector is a composition of what vectors. And this measurement is extremely tough because the product is F3 minus the difference and F3 plus the difference. And I probably forgot to mention, and I should not forget it, that we're talking about 2 signals that are 1 megahertz separation. And that's a very, very tough measurement to keep the noise level down. Therefore, we are introducing a duplexer, which is 1 megahertz duplexer, to combine the signals. And we're introducing a new device, old device, a BEMPAS bandstop. This is just 2 megahertz apart. So now using this combination, we are fulfilling the task. And now, as you can see, the flow is maintained. The TX1 and TX2 are terminated here. The jammer goes into the device under test. But before going into the spectrum analyzer, takes the bypass route, and now he is terminated, and now we believe this is the highest dynamic range that you can achieve. Let's switch into the roadmap of a test rack system. Everything we said thus far can be combined, connected with a switch matrix, put firmware, control it with a server, and you get yourself an automatic test equipment that can measure your device on the test. So our sister company is Dow-Key Microwave, located in California. They are making coaxial switches, and these are the synergy between the companies and the products that are being manufactured. Switch matrix is offer you the flexibility, or reconfigurable and expandable, and the interface options are Ethernet, LabVIEW based, RS-232, etc. More information can be found on this presentation or contacting their facility. These are customized solutions, low PIM test solutions that we did, and combining their expertise and our expertise yield a very good product. This is a coaxial switch PIM data, and as you can see, it's well below the 160 dBc line. Again, examples of the design that we are capable to produce and interface options. I'm kind of ready for questions. So if anybody has a good question, then I would like to take it.
Okay, great. Thanks for that nice presentation, Rafi. Excellent job. The first question is the test setup 3. There is a low PIM termination at the output of the BRF diplexer. Why is this done? The IMD tones created will be created at a low level and will be rejected by greater than 50 dB by the BPF at the output diplexer. Would that be enough?
You're right. There's really no absolute need to put a low PIM termination at this port. There's no absolute need. It all depends, though. Let's run the numbers. Minus 140 dBm, third IMD, and let's say we have plus 26, and let's say that we put nickel, simple termination with nickel connector, ferromagnetic. If you run this, if the rejections are fine, then I would say that here you don't have to. Past experience show that sometimes you do, sometimes you don't. Depends on what it is you're trying to measure, and depends on how much different will be the IMD generated here than the IMD generated device on the test. There's really not 100% need to do that here. Next.
Okay. Next question is, what is the source of the 2.2 dB per dB as opposed to theoretical 3 dB per dB? Doesn't that significantly change the calculation?
These are empirical values that I gathered from experience when dealing with test setups that are based on filters. And the reason is the narrow band, the filter is narrower band than a hybrid or an attenuator. And I want to say that I want to believe that this rate change is due to the extra delay the signals are going through. So I'm using the 2.2 empiric and I found it to be quite accurate. But it's an empiric number. Next.
Okay. Next question. As you mentioned, phase can be critical to the measurements. Is there a method to check all the phases that can be encountered?
Usually it's being done by my customers. So they are the one that might, as you can see, I did not include any phase shifter in my test setups. And I know that some customers, some manufacturers are using a phase shifter to find the minimum and the maximum of the result and to make sure what I'm trying to say is that you can avoid all of that by making sure that IMD sources are well separated. So I don't have information about phases that related to my setups.
Okay. Next question. In the triple beat test, is there a setup? Is it fixed or tunable across the band?
Oh, very good question. This is fixed. By the way, the worst case is when the carrier is right, the interferer jammer is right in the middle of the RX band, and therefore that's the worst case. But these are not tunable filters. They can be manually tuned to other combinations across the download band.
Okay. Does the match at the BPF BRF at the F1 plus F2 affect the IP3 measurement?
Yes. Yes, indeed. Every time the match, match I mean VSWR wise. If somebody means something else, I'd like to know. But for me, match means VSWR. There are two ways to manufacture that diplexer. They can cross over each other at 3 dB points, and thus creating a complete S11 match port. What we found out that the sliver of frequency band customers can tolerate, and leaving a little bit of transition band in terms of the S11 match did not really harm the setups.
Okay, great. I think we've answered all the questions for now. You guys have really developed some innovative and timely products, so I really appreciate K&L sponsoring this webinar today, and you gave us some great information. This presentation will be archived for viewing later on the Microwave Journal website in the events section, and there'll be a PDF of this presentation that will be emailed out to everybody who registered after this close of this webinar. We thank everybody for attending, and Rafi, thank you very much for a great presentation.
Thank you for everybody.